Welcome back, everybody. Learning as a hobby here. I want to go over the exercise set for section 2.1 in the Taylor Classical Mechanics book in this video. So let's jump into it. There's only a few questions and they're relatively short, so this shouldn't take that long. All right, so question 1 says, when a baseball flies through the air, the ratio of the quadratic to the linear drag force is given by 1.6 times 10 to the third second per meter squared times the diameter of the baseball times the velocity. Given that a baseball has diameter 7 centimeters, find the approximate speed v at which the two drag forces are equally important. For what approximate range of speeds is it safe to treat the drag force as purely quadratic, and under normal conditions is it a good approximation to ignore the linear term? Answer the same questions for a beach ball of diameter 70 centimeters. All right, so the two types of drag forces are comparable to each other when the ratio of them is 1. So I just set that equal to 1, and then plug in the numbers for the baseball. Don't forget to convert the units so that everything matches. So you have to turn centimeters into meters just to make sure that all the units match. And then once you plug it into the formula over there, you solve for v, and that gives you that v is approximately 0.009 meters per second. So very small quantity for the velocity. And that means for, this situation, the linear term is practically 0, so it's safe to ignore it. All right, and then the range of values for which you can do this is anything greater than 0.009, because that will be when 0.009 meters per second, because that will give you a ratio that's bigger than 1. Okay. But since that's such a small speed under normal conditions, in most cases you can ignore the linear term for something like a baseball. All right, for a beach ball, it's even the linear term is even more negligible. If you do the same calculation, you'll see that v has to be 0.0009 meters per second, which means that in this case, the quadratic drag is really what dominates in that situation. All right, that's basically question number 1. All right, let me read out question 2. The origin of the linear drag force on a sphere in a fluid is the viscosity of the fluid. According to Stokes' law, the viscous drag on a sphere is F subscripted ln equals 3 pi eta times d times v, where eta is the viscosity of the fluid, d is the sphere's diameter, and v is its speed. Show that this expression reproduces the form F ln equals bv, with b equals beta d. Given that the velocity of air at STP, meaning standard temperature and pressure, is eta equals 1.7 times 10 to the minus 5 Newton seconds per meter squared. Verify the value of beta given in section 2.1, which was this quantity here. Beta was 1.6 times 10 to the minus 4 Newton seconds per meter squared. Right, and then he has actually a note to this problem here. The viscosity eta of a fluid is defined as follows. Imagine a wide channel along which fluid is flowing in the x direction, such that the velocity v is 0 at the bottom, y equals 0, and increases toward the top, y equals h, so that the successive layers of fluid slide across one another with a velocity gradient of dv dy. The force F with which an area A of any one layer drags the fluid above it is proportional to A and to dV dy, and eta is defined as the constant of proportionality. So in other words, F is eta times A times dV dy. So that gives you the definition of this term eta. Okay, so here's the solution to the problem. If you let beta be the number 3 pi eta, then since eta is a fixed constant for a particular fluid, beta is 3 pi times 1.7 times 10 to the minus 5 Newton seconds per meter squared, which gives you that beta is 0.00016, and the decimals go on, which is so this is approximately 1.6 times 10 to the minus 4 Newton seconds per meter squared, which means that the linear drag force is 3 pi eta dv, or in other words, that's the same thing as beta times d times v, which is the same thing as bv, where b is beta times d. So that's basically it. All right, that's question number 2. All right, question 3, part A. These problems are actually take longer to read than they do to actually solve. But part A says the quadratic and linear drag forces on a moving sphere and a fluid are given by the quadratic drag forces kappa times q times a times v squared, and the linear drag force is 3 pi eta times d times v. Show that the ratio of these two kinds of drag force can be written as r over 48, where the dimensionless Reynolds number r is given by the formula dvq over eta, where d is the sphere's diameter, v is its speed, and q and eta are the fluid's density and viscosity. Clearly, the Reynolds number is a measure of the relative importance of the two types of drag. When r is very large, the quadratic drag is dominant and the linear can be neglected, and vice versa when r is very small. All right, and there's part B also, but let's do part A first. And actually, do I need this note for part A? Let me read out the notes. So the note says the numerical factor 48 is for a sphere. A similar result holds for other bodies, but the numerical factor is different for different shapes. So here we're just focusing on a sphere. Note 2 says the Reynolds number r is usually defined as dvq over eta for flow involving any object with d defined as a typical linear dimension. One sometimes hears the claim that r is the ratio of the quadratic drag over the linear drag. Since that ratio equals r over 48 for a sphere, this claim would be better phrased as r is roughly the order of the ratio of the quadratic drag over the linear drag. Okay. So here's the solution for part A. So taking the ratio, using the formulas, we have kappa q a v squared over 3 pi eta dv, and using the fact that this is a sphere, the diameter is double the radius, so the radius of the sphere is d over 2. So A would be the cross-sectional area would be pi times d over 2 squared, right? Pi r squared. And then just simplifying everything, you get, and then rearranging in a convenient way, you get dvq over eta times kappa over 12, which gives you the Reynolds number times kappa over 12. And he does say it actually in the next problem that for a sphere, kappa is equal to 1/4. So just plugging 1/4 in for kappa and simplifying, you get that the ratio of the quadratic drag to the linear drag is r times 1 over 48, right? 1/4 times 1 over 12 is 1 over 48, which gives you the Reynolds number over 48. And that's basically it. Okay, and let's see what part B asks us to do. Find the Reynolds number for a steel ball bearing diameter 2 millimeters moving at 5 centimeters per second through glycerin, which has density 1.3 grams per cubic centimeter and viscosity 12 Newton seconds per meter squared at standard temperature and pressure. All right, so this is just a calculation. You just plug the numbers into the formula that we just derived. So here, D is 2 millimeters, V is 5 centimeters per second, and so on and so on. You have to make sure that you convert everything into the correct unit. So I turned all of the centimeters into meters and the millimeters into meters and so on. I turned grams into kilograms. And once you have everything, then you can figure out what the Reynolds number is. You just plug in the values. And in this particular case, you get something that's approximately 0.011. So, or in other words, 1.1 times 10 to the minus 2. There's no units attached here. The Reynolds number is unitless. So, okay, and that's it for question number 3. And last problem here, question 4. The origin of the quadratic drag force on any projectile in a fluid is the inertia of the fluid that the projectile sweeps up. And then there's I think there's 3 parts to this one. So part A says, assuming the projectile has a cross-sectional area A, which is normal to its velocity, normal meaning perpendicular, right? It's traveling perpendicular to the velocity, and speed v, and that the density of the fluid is q. Show that the rate at which the projectile encounters fluid, with the rate being mass over time, is QAV. Let's do that first, and then we'll look at the other parts. All right, so for part A, just writing down what they gave us, the cross-sectional area is A meters squared, let's say, velocity is V meters squared, and the density is Q kilograms per meter cubed. Every second that the projectile moves through a change in volume of AV cubic meters per second, right? It's just A times V. That tells you the volume. Multiplying, the change in volume every second. So multiplying by the density of the fluid tells us how much fluid is displaced every second by the projectile, which is just AV times Q kilograms per second. So that's the change in mass of the change in time. And that's the answer for part A. Right, part B says, making the simplifying assumption that all of this fluid is accelerated to the speed v of the projectile, show that the net drag force on the projectile is QAV squared. And then he has a little note here about this. It is certainly not true that all the fluid the projectile encounters is accelerated to the full speed v, but one might guess that the actual force would have the form F quad equal kappa Q A V squared, where kappa is a number less than 1, which would depend on the slope of the projectile. I'm sorry, with the shape of the projectile, with kappa small for a streamlined body and larger for a body with a flat front end. This proves to be true, and for a sphere, the factor kappa is found to be 1/4. Right, so that's why I used 1/4 for kappa in the previous problem. So let's look at that one next, and then the last part is C. So, all right. So for B, from part A, we know that the change in the change in mass over the change in time is A times Q times V. If you look at the change in momentum over time, you get delta M V2 minus delta M V1 over delta T. V2 is the velocity at time 2, and V1 is the velocity at time 1. Here you can just break it up into the change in the two momentums, which gives you the formula A QV2 times V2 minus AQV1 times V1, right? Because delta M over delta T is AQV in both cases. So, and then delta M times delta V over delta T is equal to, just simplifying, AQ times, in parentheses, V2 squared minus V1 squared. That gives you the net drag force for any two velocities. But here, assuming that V1 is 0, so I'm assuming that the projectile is moving through a stationary fluid, and V2 is V. So at time 2, assuming the projectile has accelerated all of the fluid that it encounters to the same velocity V, then plugging those numbers into the formula above gives you that the net drag force is delta M times delta V over delta T. Remember, that's mass times acceleration is force, right? And that's equal to AQ V squared, because V2 is V and V1 is 0, right? And that gives you the formula that he wanted us to derive. Okay, and then last part C, is this one is just a calculation problem. Show that the quadratic drag force is kappa QAV squared, reproduces the form F quad equals CV squared with C equal gamma D squared. Given that the density of air at standard temperature and pressure is Q equals 1.29 kilograms per meter cubed, and that kappa is 1/4 for a sphere. And then he wants us to verify that gamma is 0.25 Newton second squared per meter to the fourth. All right, so that's the last part. So let's do that here. So just using the formula, so F quad is kappa QAV squared, which, again, using the fact that we're dealing with a sphere, A is D over 2. So that's the radius, right? So A is pi r squared, or pi times D over 2 squared. And simplifying everything, we get kappa Q pi over 4 times D squared V squared. And that means that gamma is if you let gamma equal kappa Q pi over 4, then the quadratic drag force, it has the form gamma times D squared times V squared, which is equal to CV squared, where if you let C equal gamma times D squared. So it just has the form that you want. So letting kappa equal 1/4 and Q equaling 1.29 kilograms per meter cubed, and remembering that newtons are in the have units kilogram meters per second squared. Then gamma, just using the formula that we have for gamma above, gamma is 1.29 times pi over 16, which is approximately 0.25 kilograms per meter cubed. And then just manipulating the units just to get, so we get what we want. You can multiply by meters to the fourth over meters to the fourth. That doesn't change anything because it's like multiplying by 1. And same thing with the seconds. That's the same thing as second squared over seconds. You multiply by second squared over second squared, which is like multiplying by 1. But then rearranging the units in a convenient way, we get that gamma is equal to 0.25 kilogram meters per second squared times second squared over meters to the fourth, which is what we want, 0.25 Newton second squared per meter to the fourth. And that's essentially the problems. It's like I said, it was relatively straightforward. These problems very short, but that's because 2.1 was kind of short. So we'll in the next video, let me stop the screen share. In the next video, I'll do section 2.2, and the exercises for that we'll do in the video after that. And once we finish, chapter 2 is kind of short. So once we finish chapter 2, I'll get back around for the people that are waiting. I'll get around to finishing chapter 1 in Simmons, and we'll get around to finishing chapter 1 in Schifrin. All right, guys, thanks for watching. Please do like and subscribe if you enjoy the content. Let me know what you think in the comments, and also keep an eye out for those new videos. And until that time, I'll see you guys then, and keep learning.